Welcome to the course Introduction to Probability Theory and Statistics. We are in topic 11, testing of hypothesis. We have already covered one lecture on different concepts of testing of hypothesis, starting from null and alternate hypothesis, Neyman Pearson theorem, and also we have done testing of hypothesis regarding population mean. This is a lecture 2 of the same topic. So, I am trying to cover testing of hypothesis regarding the population variance and the population distribution. If possible, I may do the testing of hypothesis regarding the contingency table. The remaining part will go to the third lecture, that is a testing regarding proportions as well as the analysis of variance. This is also a very important topic as we discuss testing of hypothesis regarding the population mean. Sometimes our interest is on the statement or hypothesis on population variance. We start with the assumption the population follows the normal distribution with the mean mu and the variance sigma square. Both are unknown, but in this process we are not going to involve the parameter mu, we are going to involve only the sigma square, which is unknown. As I said, we start with the null hypothesis whether the population variance is going to be this value or not. We start with the simple statement for the null hypothesis, composite statement on alternate hypothesis, and later we can go for less than or equal to in the null hypothesis as well as greater than or equal to in the null hypothesis also. As I explained earlier, we have a Neyman Pearson lemma and there are so many theories involved and so on. Finally, it will end up what is a test statistics, in which you can able to conclude whether the observed or realization of a test statistics value is lies in the critical region or not. If it is lies in the critical region, then the null hypothesis will be rejected. If the value of the test statistics going to be lies not in the critical region, then the null hypothesis is not to be rejected. Since we are talking about the population variance, as you know the theory, we will identify n minus 1 times s square by sigma square, which is chi-square distribution with n minus 1 degrees of freedom. If you recall how the degrees of freedom come into the picture, that you can recall, because it involves only n minus 1 independent information, because we have provided all such n data with the sample mean. Therefore, it is going to be n minus 1 independent information, therefore, the degrees of freedom is going to be n minus 1. So, n minus 1 times s square by sigma square, that is going to be chi-square distributed whenever the population follows a normal distribution with the mean mu and the variance sigma square, that we have already derived earlier in the previous topic. So, we are going to use that statistics to conclude the statement to be rejected or not to be rejected. Whenever we say the statement to be rejected, we always talk about the null hypothesis, and always the problem started with the null hypothesis. So, there is no confusion. Sometimes the students ask which one I should consider as a null hypothesis. Null hypothesis always equal symbol or less than or equal to or greater than or equal to. Negation of null hypothesis, that is going to be alternate hypothesis. Fine. Yes. So, once you have a, so now we are coming into the third step. The first step is making the statement, second step is identifying the test statistics, and the third step is getting the values for the test statistics with the help of a sample as well as the null hypothesis. Because the null hypothesis says the population variance is going to be sigma naught square. Therefore, we supplied the sigma naught square from there, and from the sample we get the sample variance. So, that is S naught square. Then step 4, you identify the starting point of the critical region. If the null hypothesis is going to be the equal sign, then your critical region has to be divided into 2 halves with the probability alpha by 2 in the right side as well as alpha by 2 in the left side. So, if your test statistics value is going to be less than this quantity or greater than this quantity, the interval I have written, then accordingly you can identify the null hypothesis will be rejected. So, we are in the step 3. First you identify the value of the test statistics, and step 4 you identify the starting point of the critical region. If it is a two sided test, then you will have a both side the critical region will be divided into half and half. If it is a one sided test, then the starting point of the critical region will have a, if it is a 1, then you will have a right tail probability is going to be alpha. If alternate hypothesis is going to be other way around, then it is going to be in the left half. So, you can identify the critical region accordingly, either in the form of two side or any one of the sides based on the alternate hypothesis, equivalently the negation of null hypothesis also. So, this is a very simple thing, so what we have done it in the earlier. Suppose you have two independent populations, then you can go for whether both the variance are going to be same or not. So, the null hypothesis will be both the variance are going to be same. Therefore, you can think of identifying what is the test statistics related to this problem. The correct test statistics is going to be the F statistics, and once you identify the statistics, then you do the other steps, that is step 3, step 4, and then finally you conclude the null hypothesis will be rejected if it is in the critical region. And here also we have a two sided test or one sided test based on whether it is a equal symbol or less than or equal to or greater than or equal to. So, now we are going to discuss one example based on this theory. Consider this example, go through this example carefully, and then you can come to the conclusion we want to go for null hypothesis of the population variance is 0.16 and the alternate hypothesis is population variance is not equal to 0.16. Based on the theory which we have discussed, just now, you can come to the conclusion n minus 1 times s square by sigma square, that follows the chi-square distribution with n minus 1 degrees of freedom. Therefore, the test statistics is this for this example. Then you can move to the step 3, you can get the table value, then you can get the step 3 you can get the observed values, and the step 4 you can get the table value, and the step 5 you can come to the conclusion whether to reject the null hypothesis or not. Here the degrees of freedom is 23, because you have a sample size of 24, Therefore, the degrees of freedom is going to be 23. So, in step 3 you find out the value using the sample information, that is this value, and the step 4 you find out the table value, then you come to the conclusion of step 5. So, the conclusion is since the stress statistics falls between the two critical region, we fail to reject the null hypothesis that the variance is 0.16. Now, we are coming into the testing of hypothesis regarding the population distribution. That means, it is possible to create a statement on the population distribution itself. Earlier we made the statement about the population mean and the population variance with the assumption that the population follows normal distribution. But now it is possible to create a statement on the population distribution itself. Then you can come to the conclusion whether the statement can be rejected or not to be rejected in the same way from the population from the sample information with the given level of confidence. There is another name for this that is going to be called it as the goodness of fit. This test is also called the goodness of fit, because you are identifying what is the distribution which matches with the given set of data. And since we are making a testing over population distribution itself, therefore, there is no involvement of a parameter. You are not making a statement about the parameter, therefore, this is also called a non-parametric test. There are many more non-parametric tests, but this is the one of the very important non-parametric test, that is the goodness of fit. And this can be applied both of a discrete type random variable or continuous type random variable. That means, the underlying distribution of the population can be of a discrete type or continuous type also. Let me start with a simple example, then we go to the theory. We have a data and the data says the data of 150 light bulbs are taken and we got the burning time of 150 light bulbs. It is very difficult to write down all the burning time of all the 150 light bulbs, but instead of that we made a table in which the interval in which the burning time comes, how many light bulbs are coming to that category. Therefore, if you if you calculate adding all the values, you will land up 150. That means, the 150 light bulbs readings are classified into or partitioned into based on the burning time. That means, there are 47 light bulbs, those samples having the burning time between 0 to 100 hours, whatever the units. Similarly, there are 40 samples of light bulbs having the burning time between 100 to 200 hours, like that 35 and 28. If you add all, you will end up the sample of size 150. So, therefore, n is going to be 150 here. The question is, whether this sample of 150 light bulbs burning time, whether that follows exponential distribution or not. Whether the question is whether the burning time of light bulbs follows exponential distribution or not. That means, the burning time of light bulbs forms a population, and the statement is whether that is going to be exponential distribution or not. For that, we have taken 150 light bulbs burning time. From there we are going to conclude whether the statement which we are making, the burning time of the light bulbs follows exponential distribution, that can be rejected or not to be rejected with the given level of significance. We always apply the level of significance alpha also. Usually the alpha is going to be 0.01 or 0.05 or 0.1. Now I am coming back to the theory. Whenever you have such a problems, then it is possible to create the test statistics of observed information, observed frequency minus a theoretical or expected frequency whole square divided by the expected frequency of k such groups summation. The k is nothing but that means you classify the given data into k such groups. Therefore, n 1 plus n 2 plus n k, that is going to be the total sample size. So, if you create such a way, then that random variable, whenever we use the capital letter, that is a random variable, whenever we use a small letter, that is a value obtained. So, this random variable follows a chi-square distribution with k minus 1 degrees of freedom. We are summing up k such values and we are concluding k minus 1 is the degrees of freedom. There is a property in the chi-square distribution, sum of chi-square distributions, whenever those chi-square distributions are independent, then again it is going to be a chi-square distribution. So, actually without the summation, each one is a chi-square distribution with 1 degrees of freedom, but you have k such random variables. It will not be chi-square distribution with the k degrees of freedom, because the total sample is involved and the individual groups also involved. Therefore, you can easily able to get from the total sample size and k minus 1 groups, you can always get what is the size of the kth group. The what is n k, you can get it from the total sample n and what is the value of n 1, n 2 and so on. Therefore, it is going to be k minus 1 degrees of freedom, not the k degrees of freedom. Therefore, the sum of random variables is going to be chi-square distribution with k minus 1 degrees of freedom. Just for notation sake, we write d square. So, do not confuse why it is square, whether you write d square or some other notation does not matter, it is just for the notation sake. The important thing is the observed frequency, expected frequency from the theory, that comes from the null hypothesis. That means what is the distribution you assigned it in the null hypothesis, from there you compute what is the expected frequency, that is EIs, and n is the total size and k is the groups and pi is the theoretical probability of occurrence of that particular ith group, and the theoretical frequency is n times Pa. Fine. The another question comes into the picture, how many groups you create or how you create the classify the total sample into k groups. Can I go for only 2 groups or can I go for 3 or 4? What is the optimal, what is the k? How many groups, that is in your hand. So, that I am going to discuss in the remark. Fine. So, here also it involves 5 steps similar to what we have done it in the testing of hypothesis. You make out the null hypothesis, that is data follows so on so distribution, or you say that the population follows so on so distribution, not the data. The population follows the given distribution. Negation is it does not follow, that is it. There is no less than or greater than symbol, because it is just making a statement about the population distribution. Then you construct the statistics that we have already discussed, compute the value with the null hypothesis and the sample information. Therefore, we use the suffix not and identify what is the point in which the critical region comes. This is always a one sided test. The reason is there is no equal and not equal concept. There is no value in it, there is no quantitative information, it is just a statement about the population distribution. Therefore, you cannot partition the critical region into two halves. So, you keep the critical region as one side, the right hand side, it is a one sided test, and identify the point in which the right tail probability is going to be alpha with the chi-square distribution with k minus 1 degrees of freedom. Then as usual you come to the conclusion whether the null hypothesis will be rejected if the test statistics value is going to be lies within the critical region. If not, the null hypothesis will not be rejected. Whatever we have done, the same things has to be continue here also. Therefore, I have developed the concept in the easy one, the same concept we are using in the further problems also. The only one question is how to find the k, that I am going to tell you later. Yes, now I am coming to that point. You should always construct k groups such that n times pi has to be greater than or equal to 5. It is a thumb rule. Suppose you keep on creating many groups, when you compute, if the value is going to be less than 5, better you merge with the recent value. Better you merge with the neighbor groups, so that make sure that after merging in that group n times pi has to be greater than or equal to 5. That means you should not go for more k in which this n times pi is less than 5. You should avoid that. If it is more, does not matter. The more does not mean that you keep a very smaller n, all are going to be more. So, you can go for as much as n such that when it is crossing less than 5, you should stop it. You got it? You should keep partitioning the total n into n1, n2, nk such a way that whenever it is going to less than that value, n times p is less than 5, that time you should stop it. Fine? Yeah, this second one I have already told why it is k minus 1 degrees of freedom, not k. There is a possibility after you conclude, not after you conclude, there is a possibility when you say the population distribution is so and so particular distribution, there is a possibility you may not know the value of the parameter values. Either it has to be supplied or you have to find. If the parameters values are not supplied to you, that means those parameter values of the underlying distribution of the population which are unknown, then you have to estimate. So, you can use the maximum likelihood estimation concept or method of moments. Whatever the method you use, you can estimate those parameters. Once you estimate the parameters of the population which are unknown, then the degrees of freedom will go down. So, earlier the degrees of freedom is k minus 1. Now, how many parameters you have estimated with the help of data, that means your number of independent information is reducing. That is the concept behind that. Therefore, your degrees of freedom will go down by how many parameters which you have estimated with the samples, then that is going to be the new degrees of freedom. Then you have to use this degrees of freedom when you compare the step 5 or also when you identify the critical region, the point where in which the critical region has the probability, right tail probability is alpha, you have to use the degrees of freedom is that particular degrees of freedom instead of k minus 1. So, these are all the very important remarks. There is a possibility based on the problem you may have some more problems, but these are all the common problems, therefore, I have listed out. And you should remember that this course is a very introductory level course, therefore, we are not discussing many more complications for every concepts. We are going with the very simple concepts with so many assumptions, and we are going in a very introductory level. Now, I am coming back to the same example what we explained earlier. I just made that example earlier to have some illustrative idea. Now, we are going for test the hypothesis that the data represents a random sample from an exponential distribution with lambda is also supplied. That means, you do not need to estimate. That means, your degrees of freedom is going to be only k minus 1, where k is the number of groups and level of significance alpha is given to you. So, you start with the statement, then find out the theoretical frequency, that is n times pi. That means, you have to find out the probability of each interval. So, the interval is made it whatever the number of intervals, therefore, you will find out each one p 1, p 2 and so on. You do not need to compute all the p's, because once you get the pi's of k minus 1, then the kth pi is going to be 1 minus of summation of remaining 1. So, you do not, that you can verify also, because the total probability is 1. So, you do not need to compute the last one, that you can make it easily. So, here the degrees of freedom is going to be, because of 4 groups, you can go back and see the table what I have explained. So, there are 4, k is going to be 4, therefore, degrees of freedom is 3. So, from the table also we have explained in the previous topic how one can view the table in which the right tail probability is going to be 0.01 for a given degrees of freedom. So, you can identify the point, that point is 11.341. So, based on your comparison with the critical region as well as the value of the test statistics, you can conclude. So, in this problem the null hypothesis is rejected. That means the test hypothesis value, the value of the test statistics is lies in the critical region. So, the conclusion is for a given this 150 light bulbs burning time with the given level of significance, you are rejecting of the statement saying the burning time follows a exponential distribution with the alpha is equal to whatever the value is given. Obviously, when the sample is going to be changed, there is a possibility your conclusion may change. Similarly, if the alpha value changes, then automatically your critical region also changes. Here it is a one sided test. So, I should not show the both hands. So, it is a one sided test. So, once the alpha value changes, then your critical region changes. Therefore, for the same data, for the same 150 data, there is a possibility the conclusion may change, correct. Once the alpha value changes, the starting point of the critical region in which the right tail probability alpha is changed, Therefore, once the alpha changes, the critical region changes more or less, automatically the same data set, there is a possibility your decision conclusion of a null hypothesis will be rejected, that also may change. And the another change is possible if the data set changes. And now you can recall the p value, you do not need the alpha, you can identify the p value, then you can find out what is the p value in which the null hypothesis will be rejected. So, the many statistical analyses, they will not worry, they will not bother about alpha, instead of that they will be worried about the p value, that will give the conclusion whether the null hypothesis to be rejected or not. Fine. Go back and read the p value statement, and then you can understand. So, with this let me complete the lecture 2, and the remaining we will cover it in the lecture 3. Thank you.